In the name of Almighty God, I'm Asa Sankoshi, and today I want to have a review on physics theory. Today I want to go through the boundary conditions. We can also study the boundary conditions for magnetostatics in complete analogy to the boundary conditions for electrostatics. They are slightly more complicated, but luckily they are not needed as frequently as in section 2.1.5. Let's zoom into the surface of a boundary so that is it can be taken to be flat and defined parallelly as the two component vector parallel to the surface and b perpendicularly as the component normal to the surface, figure 2.16. If we put a line across the surface and evaluate using equation 2.24, we find that the normal component of the magnetic field must be continuous. B perpendicular outside minus B perpendicular inside is equal to 0. Using equation 2.25, we can integrate over a narrow rectangle around the surface to be completely general. Let's suppose that there is some current density K on the surface, and let's orient the plane of our loop to be perpendicular to the surface current. If we take the size of the rectangular perpendicular to the surface to be arbitrarily small, then we can neglect its contribution to the integral, and we are left with the boundary condition for the parallel component of the magnetic field, such as parallel outside minus B parallel inside is equal to the friction 0 K multiplied by n, where K is the surface current density and n is a unit vector pointing perpendicular to the surface from inside to the outside. A good mnemonic to remind this equation is to notice that they are sort of reverse of the analogous electrostatics. Figure 2.16 illustrates a parallel and perpendicular components of B at a boundary where surface current K flows along the boundary. Boundary condition 2.14 and 2.15, normal B becomes parallel E and vice versa, and epsilon 0 goes in the denominator while micro 0 goes in the numerator. Also note that sigma, the surface charge density, is scalar while cos surface current density is a vector. This means that sigma must be related to the scalar E perpendicular and co is related to the vector B parallelly. And now I'm going to go through the 2.2.5 work and energy in magnetostatics. Unlike electric fields, magnetic fields don't work. This can be seen immediately from the Lorentz force law 2.27. The cross product V multiplied by B means that the force is always perpendicular to the velocity. The speed of the particle cannot increase, and V doesn't work. This is the cause of much conceptual confusion, as there are many standard problems where work is being done by something, usually an external source or gravity, but it's not the magnetic field. However, magnetic fields store energy just like electric fields. UV is equal to 1 divided by 2 micro 0 integral absolute b to the power of 2, and the third order of differentiation based on the radius. This is identical to the analogous expression 2.18 for electric field, except for the prefactor. Now I want to go through the next section 2.2.6, cyclotron motion. Even though magnetic fields don't work, they can still change the direction of the charged particle's motion. The most common situation is the motion of a charge q with mass m in a uniform magnetic field B is equal to Bz. Suppose the particle moves with velocity v is equal to v y, then evaluating the cross product f is equal equal to QV, B y multiplied by Z is equal to QV Bx. The force is constant and the x direction, which is a perpendicular to the particle's motion. As the particle begins to accelerate in the x direction, the force will remain perpendicular thanks to the cross product. So what we have is uniform circular motion. A charged particle in a constant magnetic field will move in a circle confined to the plane which normal parallel to the B field. Actually, if the particle has some initial velocity parallel to the magnetic field, this velocity component will be changed because of the cross product. That's the most general motion in a constant magnetic field is a helix with the velocity perpendicular to the magnetic field v perpendicular, applying the rate roll of the v above. By using the uniform circular motion formula from selection 1.2.1, you can easily work out the radius of the circle r is equal to m divided by qb, and the angular frequency known as the cyclotron frequency omega is equal to qb divided by m. Amusingly, the formula for the cyclotron radius remains the same even as relativistic velocity is provided. We replace the numerator mp with the relativistic momentum p. See chapter 6. Now I want to go through the electrodynamics. So far we have given a treatment of how static electric fields and magnetic field behaves. The story becomes more complicated as we fill into the final piece of the puzzle and ask what happens when charge and currents, the sources of electromagnetic field, move and change in time. Now I'm going to go through the Maxwell's equation. The story is summarized by the complete Maxwell's equations. The first is delta A is equal to rho divided by epsilon 0. The next is delta B is equal to 0. And the next is delta multiplied by A is equal to minus the power differentiation um, magnetic fields based on the time. Another is delta multiplied by B is equal to micro 0 multiplied by 2 plus micro 0 epsilon 0. The differentiation of E based on the time. The only change from the static case are the time derivative terms in equation 2.40 and 2.41, which describes how to change magnetic field produces an electric field and how a changing electric field produces magnetic field. The former is called inductance and the latter is called displacement current, also known as Maxwell's corrections. 2 Ampere's law. These are the main new facts that we must account for when we deal with the electrodynamics. As it turns out, the displacement currents almost always too small an effect to be measured, so we will focus our attention on induction, which is much more practically important. Thank you so much for watching my tutorial video until the end. And today is 24th of the April 2026. Time is 12:55 a.m.